Welcome to OP-TEC, the National Center for Optics and Photonics Education. Today I would like to introduce you to the IPG fiber laser. We're looking at a laser here that is in the YLR series. This output on this laser is 100 watts. We won't be using quite that amount of energy today, but we will be looking at that. This is the console where we'll control the output power. We also can put this in modulation to where we can have a pulse come out. And our energy is delivered through this yellow cable, which is our fiber optic. Our fiber optic will leave and come into our autocollimator. This is a very sophisticated optic, so we have a collimated expanded beam. It has a bayonet connect right here, so we can connect that, and there's an interlock on this, so the laser won't operate unless the autocollimator is here. We're going to use a focusing optic here. I have a positive lens here. The focal length on this is somewhere between 45 and 50 millimeters. And we're going to put the beam through a beam splitter. And 95% of our energy is going to go down the optical rail. And we'll be reading that with a power meter. And 5% will be hitting our CCD beam profiler. And once we have a signal into our cameras, that we're going to look at the computer and be doing some beam analysis with our computer, looking at the Gaussian beam that comes out of this laser. So this will be the first part of our experiment, just to to safely propagate a signal down our signal chain, to take a certain percentage of that power off, put it into our CCD camera. We're going to operate the laser at 10%, which makes our output power somewhere around 2 or 3 watts. We'll be using a neutral density filter on the optical rail to reduce the power, as well as the CCD camera. So we'll be using all those things to safely make sure we're taking care of the personnel inside the lab, as well as the equipment that we use today. I want to take this opportunity to show you what we're doing just as safety precautions on our equipment. We've set our laser at the lowest operating percentage, which is 10%. And looking at the power meter, it tells me that I've got about a 2-watt output. So it means that I'm dumping about 95% of that 2 watts into my thermal pile, and I'm protecting my CCD camera at this particular time with this fire brick to make sure we're not hitting anything with that. And there's several controls we can have here with our laser. Want to make sure goes through the sequencing and the start sequence there. And I have the machine set to a 0% output. And this comes in handy when I want to merely look through the optical axis and see where my laser beam is. I'll hit the guide beam. This is a diode laser. It runs through the fiber optic, so I know it gives me all those general ideas of where positions of my beam's going to be and where my equipment should be. Once I've done that, I want to hit my set button, and we're going to set this to 10%. And the OK button will lock that in. It says 10% here. I still have my guide beam on, so I can look and make sure where my infrared beam will be. And once I'm satisfied and have these things set up where I want them to be, I'll hit the emission. We'll hear 3 or 4 clicks go off, and then the light will stay on, and we know we'll have laser emission. And usually at this 10% setting, I've got an output of about 2 watts. So now we have to ask ourselves, do I want to put 2 watts into this CCD camera? And the correct answer is no, I don't want to do that. So we're going to use neutral density filters, which drops all those wavelengths, drops all the power at the same level, and we will be able to reduce the power quite a bit and take a good look at that beam profile to see what it looks like. So now I'm a little bit more comfortable with 6 milliwatts and introducing that into my CCD camera. We'll be using a ND4 filter and taking a look at our beam profile. What I've done is I've taken a screen capture of our beam profile, and as you can see, we would be looking for a nice Gaussian shaped beam, and that's not exactly what we have here. We have to understand that there are several factors that are involved here, and the quality of our output beam profile depends on the type and quality of optics we are using to focus down the laser beam, the character and density and clarity of our neutral density filter, as well as quality of our beam splitter. So those are just three things I'm introducing into the signal chain that affect what the output of this beam profile looks like. I recommend with this particular unit that has a maximum output of 100 watts, you don't operate it above 10%. This will protect your personnel as well as your equipment. And you should be operating at around 2 watts at that particular setting. Also, what we want to do is calculate beam diameter as well as beam divergence. So you'll be taking your beam diameter readings at 2 different locations and calculating theta. So I would use my beam profiler and according to beam diameter and use that as much as possible so you become comfortable with the equipment and can also guide your students in using the beam profiler. What I want to demonstrate here is the power of this laser. What we're looking at is we're looking at the laser striking a fire brick operating at 47 watts. This is half power of what this laser can output. So we want to make sure you're taking every precaution to operate the laser at below 10%. You're taking measurements with your thermopiles and your photodetectors to see what you're working with. And if I were to leave this on, this laser would be able to penetrate this brick all the way through. So make sure you're practicing laser safety as you are operating a Class 4 locked laser lab. In data table 3, we're referring to pulse to energy. I would consider this part of the lab as optional because one of the things is it requires some additional input on your part. You'll need to refer to the operator's manual, and you'll find that there's pinouts and descriptions of what you need to do with the RS-232 port and interface it with the computer in order to operate this in pulse mode. Once you've taken care of that, you want to be able to record your information using a fast photodiode. I have a fast photodiode here which was designed by one of our students, and it's input into an O-scope so I can capture those with a digital storage scope. You can buy these off the shelf, commercially available. Refer to specific wavelengths to decide which one you want to purchase. This is an excellent lab to do. It requires some additional wiring of your laser as well as interfacing fast photodiodes, O-scopes, digital storage. Overall, this is an excellent lab, but it will require some additional technical expertise and overall time. So take that all into consideration when you're scheduling labs and requiring students to interface with the equipment and the lasers.